Hello there, ATS 572 students. Dr. Shragi here, and I just want to walk through another block of reviewing with you for the final. And right now, what we're going to be going through here is the material that was about cyclogenesis and the development equations. This was all stuff that was in the first module of the second semester of the course, and I think this is something that we should be able to review fairly easily in this sort of online format. Remember, we have to have a definition of what we mean by cyclogenesis and cyclolysis, and intuitively we have some ideas from lecture 3 about how cyclogenesis is about how pressure is falling and vertical motion is positive. Well, W is positive, omega would be negative. Relative vorticity is increasing, that is moving farther to the right on the number line. Cyclolysis, on the other hand, would be pressure is rising, vertical motion W is negative in Cartesian coordinates, omega would be positive in isobaric coordinates, and relative vorticity is decreasing. By that sense, we mean as in moving to the left on the number line. So an anticyclone is getting stronger, a cyclone is getting weaker. We talked briefly about the idea that there was rapid cyclogenesis as well. Actually, I'm not sure that any of these definitions would necessarily be on the final, that we have plenty of other material to talk about on that day. Now, in our first part of Module 1 of ATS 572, we really were picking apart this idea of vorticity and vorticity equation and so on, and we looked at all these terms like tilting and stretching and so on. But that's only part of the story here. It turns out if you actually start looking at those equations, it's hard to look at that vorticity equation and figure out, okay, based on this weather pattern, will we have cyclogenesis or will we have cyclolysis and so on? Turns out we have better tools for such things, namely things like the development equations. And we had 4 development equations: the height tendency equation, the Peterson-Sutcliffe equation, the Hirschberg-Fritsch equation, and the Zwack-Akasi equation. All of which we did things like derivations of, but that would obviously not be appropriate material for a final. Even really what were their underlying assumptions about things like, their development started with the vorticity equation and moved on to the thickness tendency equation in the case of the height tendency equation and so on would be much too difficult, I think. Rather, though, we can, same with obviously you wouldn't be expected to memorize these equations or something like this. I can tell you from in the past, it's often the case that the front page of the ATS 572 tests just have all the equations on them, and that way you don't have to memorize them or anything like that. This is the height tendency equation in quasi-geostrophic form. And we went through and actually talked about all these terms. Like, for example, that left-hand side of the equation, well, you can see height tendency there, the change in geopotential with respect to time, that it's actually the 3D Laplacian of that. So this is actually looking for the maxima and minima of height changes. And so anytime this term is going to be greater than 0, we're going to be looking at a region that is a maximum of height falls, whereas if that term was negative, that will be the case when we're at a region that is maximum of height rises. And so when you start picking apart the interpretation of the height tendency equation, you have things like the advection of absolute vorticity. It happens to be by the geostrophic wind, but that's no big deal. Okay, so you have advection of vorticity. It's important to understand here that this is advection of vorticity at that location. So, like, other development equations are going to talk about like advection of vorticity at the level of non-divergence, or the integral of vorticity advection. This is much simpler than that. For the height tendency equation, the pattern of height rises and height falls are going to just depend on the advection of vorticity on that at that level. So if you're talking about like the change of the height of the 500 millibar surface, then this is advection of vorticity at 500 millibars. If you're talking about changes in the height of the 850 millibar surface, then this is changes in vorticity. This is vorticity advection rather on the 500 millibar surface. Moving on to the 10th slide here. Oh, by the way, back on the 9th there was also that beta term here. We'll be seeing so much about that beta term in this review, but there is a beta term here in this height tendency equation. Moving on to the 10th slide here. The interpretation of the height tendency equation shows us how, we can have areas of positive vorticity advection and so on. They're going to result in height falls, which makes the height of the like in the area of positive vorticity advection, the heights are going to fall, which makes the trough move farther to the east and so on. And in the area of advection out ahead of the ridge, we're going to have the heights rising and so on. And you can actually work through like the signs and the magnitudes of this if you had a shorter trough, the shorter wavelength trough and ridge, or a longer wavelength trough and ridge. And you can see that this all turns out to be very consistent with what we learned about Rossby waves in another module of the course, where short waves are going to have big gradients of vorticity, so they're going to have big values for their vorticity advection, which is going to make for large height falls and rapid propagation of the trough. Whereas for long waves, the vorticity gradients are small and the heights are going to rise. I'm sorry, you can read through the slides here. It's a little hard for me to see on this small screen that I'm doing this on. But what you're going to see is this is all consistent with the ideas of how Rossby waves work that you learned about in the second module. There are more terms in the height tendency equation. Like, for example, there's a temperature advection term and there's a diabatic heating term. But notice that it's actually partial P of temperature advection and partial P of diabatic heating. It's how temperature advection changes with respect to height and how diabatic heating is changing with respect to height. And you will need to want to know these basic rules here that, like, according to the height tendency equation, warming increasing with height or cooling decreasing with height. Which one of these is the one that's going to actually happen? Well, most of the temperature advection happens at low levels of the atmosphere. So whether you're talking warming or cooling, you want to have that decreasing with respect to height. So knowing that cooling decreases with respect to height leads to height falls. Warming decreasing with respect to height leads to height rises. And let's see, there's some other terms here. I don't think that last term right now is something we would be sweating about. It's this diabatic heating term. All right. So we kind of have some basics of like, what do we need to know about the height tendency equation? Mostly we need to know how to interpret the different terms. Which terms would be leading to cyclogenesis and cyclolysis under different circumstances. Now, if we switch gears over here to from lecture 5 of this semester, we're going to start talking about the Hirschberg-Fritsch equation. Now, one of the most important things to remember about the Hirschberg-Fritsch equation is that this is the one that makes that so-called lid assumption, where we are making the assumption that we're talking about a layer of the atmosphere and the top of that layer is not going to move. So we're really actually talking about the bottom of the layer, a level that makes the bottom of a layer of the atmosphere and the top of that layer is not going to move. Now, this is a tricky assumption. Hirschberg and Fritsch are saying that basically there's some height above the ground at which the passage of cyclones and anticyclones and things like that at the surface is no longer changing the geopotential height. Well, that's probably true. It's hard to know exactly where in the atmosphere this lid would actually be. Now, we went through like 20 slides to actually come up with our derivation of the Hirschberg-Fritsch equation, which in and of itself is not terribly important. And again, I wouldn't expect you on slide 17 here to actually like be able to recognize, or like memorize the Hirschberg-Fritsch equation. But knowing what all these terms mean here. I mean, the Hirschberg-Fritsch equation is fundamentally telling us here on slide, which one are we on here? 18, that the changes of the height of this level that we're calling the bottom of our layer are due to the temperature changes that are happening inside the layer. Notice that we are integrating from the top to the bottom of the layer, things like temperature advection, diabatic heating, adiabatic heating, and so on. And so, according to the Hirschberg-Fritsch approximation here, as long as these assumptions are right, then it's only what's happening above our level that's going to be determining what is how the heights are going to be changing at our level here. So it's only like the temperature advection, the diabatic and adiabatic processes above our level that matter according to Hirschberg-Fritsch. Now we can actually work through and like talk about a layer that is warming by temperature advection or diabatic heating or whatever, and you could work through the signs and you'd find out that warming above our level means that the level itself is going to fall. Now, it's easier to see that with these little cross sections that I made here. I've got two little levels of the atmosphere. We're calling them bottom and top. And if I had some kind of warming inside of the layer there, well, all kinds of places in your atmospheric science education, we showed how that layer will then expand. I'm showing it kind of bowing up and bowing down, but that can't actually happen in the framework of the Hirschberg-Fritsch equation because we've made a lid assumption. The top of the layer can't move, But we still want that layer to expand, which means if we have warming above our level B, like ZB and PB or whatever there, then that makes that layer bow downward closer to the ground, and we have effectively cyclogenesis due to this warming above the ground. In the same sort of way, if you have cooling above our height B here, then that effectively, as we pull the layer up higher and we get higher heights near the surface here. Now, this is not to imply that heating is equally important in all places in the atmosphere in the Hirschberg-Fritsch development. In the Hirschberg-Fritsch development, there is that dP over P term. You can actually rewrite that integral to be in this sort of form where you have all those heating terms like temperature, advection, adiabatic processes, and diabatic processes with pressure in the denominator like that, and you have that inverse pressure weighting term here. So you have warming divided by P at every one of these layers in the atmosphere, but since P is getting smaller and smaller and smaller, you're dividing by a smaller and smaller number the higher up you go. The same amount of warming at any particular altitude is going to be resulting in a bigger change in the geopotential heights the higher up it happens, because you're dividing by a smaller number of P there. So like if I took some amount of heating and I applied it on here on slide 27 to these lower levels of the atmosphere, they'd be dividing by a certain value of P, which is going to be a fairly big number here. It would be nowhere near as effective if I took the same as if I had taken the same amount of heating and it happened up higher near the top of my lid up there, where I'm dividing by a very small layer. Now, in practice, most synoptic scale heating actually happens very near the surface. I mean, temperature, advection, latent heat release, and so on typically happen, in the lower troposphere. So most of that heating is actually going to be happening below whatever we're considering this level. Let's say this bottom of our layer here is 500 millibars or something like that, or 850 millibars or 700 millibars or something. No matter what, most of it is happening below down there. But that's actually where Hirschberg-Fritsch says it matters least. Rather, what we need to look for is like deep layers of convection or advection or latent heat release or whatever that extend their warming up into our layer that we care about, up above the height that we're trying to figure out if that's getting closer to the ground or farther from the ground. And in fact, the higher and the deeper it can get, the better in terms of its effectiveness at changing the heights, under the assumptions of the Hirschberg-Fritsch approximation. And that's always important to understand it. All of these approximations and all of these development equations are only as good as to what extent the real situation at any given time is matching their approximations. Okay, well, another group of researchers took it a different direction, and they ended up with the so-called Pedersen-Sutcliffe equation. Now, to understand the Pedersen-Sutcliffe equation, which came to us from lecture 5, you need to know about this idea of the level of non-divergence, and we drew a number of different diagrams here where we showed, like on the right here, we showed a curve that shows the profile of divergence in this area, where like at low levels I'm having convergence, so the divergence term there is negative, and then at some height above the ground I'm hitting an area of zero divergence, and then up above that height I am having positive divergence. And, we could talk about like in an anticyclone kind of situation. But either way, we could define some kind of level of non-divergence here. Now, in practice, that's hard to do. In a real world situation, it's actually very difficult to decide at what height above the ground the level of non-divergence is happening. But mathematically, it makes perfectly good sense. And again, if you take a large number of slides, you can actually work through the derivation of the Pedersen-Sutcliffe equation, which there is no way I'm going to be expecting you to do or anything like that. And in fact, I wouldn't even expect you, of course, to memorize these equations. The idea would be that you would be doing things with them. They would be in some sense provided to you. And we would also be picking apart what all these different terms mean. Notice that the left-hand side is another way of talking about cyclogenesis. It's a little tricky to see how this is cyclogenesis. I mean, it's change in vorticity with respect to time, but more specifically, it's change in geostrophic vorticity with respect to time. This means like geostrophic vorticity, remember, is about the shape of the contours of pressure. The geostrophic vorticity means, like we have closed areas, lower pressure, closed areas of higher pressure, because it's describing to what extent the wind as it follows these contours is rotating. So this is basically a measure of like how much we're making closed isobars on the map. It's a measure of cyclogenesis. And it depends on all this other good stuff here. Now, the farthest right part of this term here on slide, where are we at here? 37. Well, it looks kind of familiar. I mean, it's got like a temperature advection term. It's got an adiabatic processes term there with stability times vertical motion. It's got Q dot, which is a diabatic heating term in it. Looks pretty good, but it's important from Hirschberg-Fritsch in a couple of major ways. Hirschberg-Fritsch said that it was heating inside of our layer between the pressure of the bottom and the pressure of the top of our layer, where top pressure of the top is basically the top of the atmosphere or that lid or whatever. On the other hand, hold on just a second here. There we go. The Hirschberg-Fritsch, the Peterson-Sutcliffe equation is saying that it's the distribution. See the Laplacian there? It's the Laplacian, or the distribution of heating between the surface and the level of non-divergence that's changing vorticity at the surface. So they're important. They're actually important in two different ways here. There's two important differences between the two of them. They have different left-hand sides between these two different versions of the equation. Hirschberg-Fritsch is about changes in a geopotential height. Peterson-Sutcliffe is about changes in the distribution of the contours at the surface. Are we making closed lows? And they have different ideas about how we get there. The Hirschberg-Fritsch equation says it's about heating from there up. And the Peterson-Sutcliffe equation says it's about the distribution of heating. Are we at a maximum of heating to make this happen? And at first that might not seem like such a big deal because the Hirschberg-Fritsch equation, we could have just called the surface of our equation the bottom of the layer. We could have made the level of non-divergence the top of the layer, and things wouldn't have seen all that difference. But that Laplacian, that's hard to get around. Now, if we had something like horizontally uniform heating, that is, the Laplacian of the heating is 0, we have the same amount of heating everywhere on the map, the Laplacian of a constant field is 0. And so, according to the Peterson-Sutcliffe development, uniform heating doesn't make any kind of cyclogenesis at all. Now, to understand why that was, we made these sort of maps with a little bit of perspective here, where I tried to make like a column of the atmosphere that had non-uniform heating, where there was more heating in the middle and less out towards the edges, like we're at some place where maybe there's latent heat release in a column of air or something, versus on the right there, you can see the more uniform heating pattern. And we walked through this in quite a bit of detail in the lectures there. If we were trying to think about this in the context of Hirschberg-Fritsch, well, Hirschberg-Fritsch tells us that the height of some level, which I'll call that, that's my height ZB, the bottom, and I've got it labeled there with some arrows there, which sort of could have been the height of, whatever, the pressure at the surface. Let's not worry about that notation there. Then the Hirschberg-Fritsch equation says that the height of that level doesn't depend on anything that's going on below that level, ZB. It's all about just the heating between ZB and whatever we call the top. I see I have a mistake on the slide. That's just in ZT up there. But it's between there and the top of our layer. And the Hirschberg-Fritsch equation tells us the height of that level depends on the amount of heating going on, but not how that heating is distributed. How it's being distributed horizontally doesn't matter. In the case of these plots here, they both would have had height falls. Both of those plots over there, the left column and the right column, both have heating above my level ZB. So they would have both required that layer to expand. Since we can't move the top of the layer, both of them would have lowered ZB closer to the ground. They're saying that distribution of heating doesn't matter. Well, maybe. But what the Peterson-Sutcliffe tells us about the terms here is different. In Peterson-Sutcliffe, we're saying, what is cyclogenesis at the surface doing in terms of geostrophic vorticity? Peterson-Sutcliffe equation says that at the surface, then, it's going to depend on the surface, the heating between the surface and the level of non-divergence. But more specifically, it's not just the heating that matters, it's the distribution of that heating. If we have uniform heating, we don't get any changes in the pattern of the contours at the surface in terms of like having more cyclogenesis going on or something like that. Geostrophic vorticities at the surface are only going to have changes at the surface, like formation of closed contours and so on, are only going to happen if the heating above it is non-uniform. If there's a localized area of heating with less heating away from there, the way I have it drawn on the left-hand side of the screen there. Like in the Hirschberg-Fritsch equation, the Peterson-Sutcliffe equation has that inverse pressure weighting term, and that means that the maximum of heating aloft is more effective I'm sorry, that means that a maximum of heating aloft is more effective at increasing geostrophic vorticity at the surface than a maximum of heating closer to the surface. Again, this is about this idea that we're dividing by P, and P is a big number near the surface, and it gets smaller and smaller the higher up the level of non-divergence is. So if we had some latent heat release or absorption of radiation or a big thick layer of temperature advection, the thicker and the bigger and the higher up in the atmosphere we can get that to happen, the more effective it is at affecting cyclogenesis. Now, the good news about Pedersen-Sutcliffe is we didn't have to make that stupid lid assumption. And the lid assumption's a hard pill to swallow, so we don't want to make that assumption if we don't have to. On the other hand, we did have to make some assumptions about the fact that we had some kind of level of non-divergence. We had to assume that there was a level of non-divergence, that we could find it, and that we were assuming that there was convergence at low levels and divergence aloft, all of which is complicated. In the real world, there's often multiple levels of non-divergence that are hard to find. It's not a simple thing to actually do this. But why does the heating need to be a maximum for cyclogenesis at the Pedersen-Sutcliffe equation when it didn't really matter whether it was a maximum or not? It was just uniform heating in the Hirschberg-Fritsch. Well, this has to do with the fact that the two different equations have a different idea of what they mean when they say cyclogenesis. The Hirschberg-Fritsch equation is just saying about changing heights of an isobaric surface. Here's the height of my 500 millibar surface. If it gets closer to the ground, that's cyclogenesis. If it gets farther from the ground, that's cyclolysis. But do you agree with that? I mean, for example, if I had just a map here, and I have these height contours here, all right? So here I have a whole bunch of height contours. You can see the labels on the right-hand side there as to how high each of them are. If I just put a uniform amount of heating over this whole region right here, according to Hirschberg-Fritsch equation, all of those areas will have height falls, and they'll all form uniformly. So all my heights in this case, I just sort of subtracted 120 meters from them, and they're all just lower height than they were before. Hey, wait a minute. Is that what you call cyclogenesis? Like the whole thing just got lower? No, there's no. We mean by cyclogenesis, we mean like we're forming a low or we're forming a trough or whatever. Now, that Hirschberg and Fritsch weren't fools, okay? They would say that's not really a problem because in the real world there wouldn't be uniform heating over some giant area like the size of the United States. There would be an area where there was more heating. That's where we'd be looking for the height falls, or there would be an area where there was uniform cooling, and that's where we would look for the height rises. So, I mean, they're not being stupid here. They're saying you'll have the sense to work this out. You won't really be talking about uniform heating over the whole globe or something like that. But in fairness, the Pedersen-Sutcliffe development does get to this point more directly. Now, the Pedersen-Sutcliffe equation describes cyclogenesis or development in terms of geostrophic vorticity of the surface, talking in terms of these closed isobars and so on. And in order to get closed isobars, you need the heights to fall more in one place and less than the other. This is why you need that non-uniform heating. Notice, by the way, though, we've spent so much time on the right-hand side, the farthest term over there, all those temperature advection, adiabatic temperature changes, and diabatic temperature changes. But with blue here, I've got it marked the vorticity advection. See, that's an advection, negative v dot del eta. So that is advection of absolute vorticity. The Q means it's using the quasi-geostrophic wind. That's fine. And it's at the level of non-divergence. So notice that the development of geostrophic vorticity at the surface depends only on the absolute vorticity at the level of non-divergence in the Pedersen-Sutcliffe equation, which in practice on synoptic scales, the level of non-divergence is typically somewhere near the 500 millibars level, which is why when you pull up a 500 millibar chart, it typically has contours of height, so that you can, get a sense of what the quasi-geostrophic wind looks like, and absolute vorticity, so that you can see, based on how they're crossing and how you get the little solenoids and everything, you can find areas of positive vorticity advection and negative vorticity advection. I mean, yeah, you're right. The level of non-divergence might not exactly be at 500 millibars, but it's usually pretty close to that on synoptic scales. So, yeah, I mean, actually, this is sort of a little shortcut, isn't it? We're kind of seeing how the Pedersen-Sutcliffe equation, this contribution to the formation of cyclones at the surface depends just, in this case, on vorticity advection at the level of non-divergence. Now, one other set of researchers would slightly disagree with that. This was the so-called Zwack-Akasi equation. And we spent a bunch of slides making the derivation. Again, I'm not going to expect you to do the derivation. I'm not expecting you to memorize the equation or whatever. But we have to work with the equation about this Zwack-Akasi equation. This happens to be the quasi-geostrophic form of it. What does the Zwack-Akasi equation tell us that we did not already know? Well, there's some differences in the terms here. Notice the role of vorticity advection in our development. The Pedersen-Sutcliffe equation, remember I just said positive vorticity advection turned out to be only important at the level of non-divergence. Zwack-Akasi says positive vorticity advection is equally important at all levels of the atmosphere. Notice that in this equation here, we've got on the top line of the equation there, we've got a negative v dot del eta. That's the advection of vorticity. And we're integrating that from the pressure at the top of the atmosphere to the surface. Every level of the atmosphere, above and below the level of non-divergence, contributes to vorticity advection at the contributes to cyclogenesis at the surface. Now, that is somewhat different than what we're saying with Pedersen-Sutcliffe, but Pedersen-Sutcliffe required a whole bunch of assumptions, like the ability to even find a level of non-divergence and so on. Here, we're just saying add them all up. Where does it matter where the advection happens? It all contributes equally. In practice, vorticity advection tends to be greatest in the mid-troposphere, like at about 500 millibars and so on. But in fact, let's just add it up no matter where it happened. Another thing that let's actually walk through that a little bit here. So like if I, on an ordinary weather chart, just happen to have on a 500 millibar chart some contours of heights and contours of absolute vorticity, very common on a synoptic chart, then any place where they're crossing and making those little solenoids, we're seeing areas of positive vorticity advection. And if I just zoomed in on that little region right there, okay, that's what that's going to look like, where those height contours and those positive vorticity advection contours are crossing. Now, if I just take it and I tip the map over onto its side a little bit, and I just show you, like I made a whole bunch of levels where we could be computing the positive vorticity advection at 1,000 millibars, 925 millibars, 850 millibars, 700 millibars, all the way up to the top of the atmosphere here. What's determining the amount of cyclogenesis happening down at the surface? Well, Pedersen-Sutcliffe said it's just the amount of vorticity advection happening at one place, the level of non-divergence. That's mathematically correct. It can be useful. It could be a good approximation. But if we can't actually find a level of non-divergence, or there's multiple levels of non-divergence, we've got a big problem here. I mean, like this case here, I have circled here, there's actually 3 levels of non-divergence. How in the world are we going to decide which one is the right one? According to Pedersen-Sutcliffe, according to Zwack-Akasi equation, cyclogenesis at the surface depends on vorticity advection at all the levels. Just add all them up. In the Zwack-Akasi equation, the level of non-divergence is not more important than other levels. And that's really helpful. In practice, the greatest amounts of vorticity advection tend to be found in the mid-troposphere, around 500 millibars, the level of non-divergence. But Zio says it doesn't matter. Wherever it happens, it's fine. It contributes to cyclogenesis, which is both good news and bad news. I mean, it agrees with our forecasting experience and intuition that the vorticity advection matters. I mean, right off the bat, from your experiences in synoptic and so on, it doesn't seem like it should really have to be at the level of non-divergence, although that does tend to be where vorticity advection is large. The bad news is, though, that means you have to follow vorticity advection at all levels. There's no shortcuts here. You have to look at them all. Well, what about heating? What does the Zwack-Akasi equation tell us about heating that we didn't already know? Pedersen-Sutcliffe told us that the pattern of heating mattered, where that you had to have a localized area of heating with less heating around it, and the higher up in the atmosphere, but below the level of non-divergence, you could get that heating, the better it was for cyclogenesis. Well, Zwack-Akasi equation looks the same, but it's a double integral. Now, we worked through a giant string of slides at that point in Lecture 6 to actually talk through what the double integral means. But the double integral ends up meaning that all the levels of the atmosphere end up counting about the same with those thermal terms. It wasn't like heating was more effective at causing cyclogenesis when the heating happened high in the troposphere, or heating was more effective at causing cyclogenesis when it happened lower in the atmosphere. In the Zwack-Akasi equation, it's not exactly equal everywhere, but close enough for government work. It basically means that at all levels of the atmosphere, heating is effective at causing cyclogenesis, which, once again, is both good news and bad news. because it agrees with our forecasting experiences and our intuition that seems temperature changes matter. It doesn't seem intuitively like it should be like temperature advection at 850 millibars is somehow more valuable for forming cyclogenesis than temperature advection at 300 millibars or something. Um, Although, frankly, temperature advection up at the upper troposphere is usually pretty small. But what this Zwack-Akasi equation tells us, though, is we don't get any shortcuts. We have to just compute the temperature advection at all levels of the atmosphere. Of course, computer programs and modules in GEMPAC and so on are set up to do these kinds of calculations for us. And everybody was just at this point exhausted from talking about the development equations, and everybody just naturally says, just tell me which of the 4 development equations is right. Which one of those is the one I should be thinking about when I'm making a forecast? And the answer is it does not work that way. They are all only as good as their assumptions and how well the assumptions fit what's going on. They're only as good as the data that are used, and they are all only as good as the computational methods that you've used. And as a consequence, none of them can be just thrown out. You got to think about all of them. So we could set them for all 4 development equations side by side, something like this, and say, well, what do they tell us? For example, all 4 equations have different ideas about what vorticity advection means. In all these cases, notice that cyclogenesis is about the advection of absolute vorticity, which is the same as the advection of relative vorticity plus the planetary vorticity. That's the beta effect. In all cases, notice the height tendency equation is telling us that the heights at a given pressure level depend on the vorticity advection at that level. According to height tendency equation, if you want to know what's going to happen to 850 millibar heights, look at 850 millibars for its vorticity advection. That is different than what other equations would say. The height tendency equation says that uniform vorticity advection would result in height falls, and there's different ways. Well, let's not worry about that for just a second here. Where am I at here? Sorry, I got off on a slide here. There we go. All right, so I am on slide 87. It says Pedersen-Sutcliffe and Zwack-Akasi are about cyclogenesis at the surface. And in both of their cases, notice that Pedersen-Sutcliffe says that cyclogenesis at the surface is caused by vorticity advection at the level of non-divergence. Zwack-Akasi says the vorticity advection any place in the atmosphere contributes equally well to cyclogenesis at the surface. They're just 2 different sets of approximations about such things. Now, in practice, that isn't much of a contradiction. For Pedersen-Sutcliffe to work, we had to have a LND, which can be tricky. And in practice, we usually just sort of pick some place in the mid-troposphere, and that tends to be where there's greatest vorticity advection anyway. So, it's not really all that much of a contradiction. It's just a mathematical complication. How about the roles of heating? Only the height tendency equation sees a role for the vertical profile of heating. When you're trying to memorize all these effects and so on, you'll notice this is the only one that talks about like cold air advection decreasing with height or warm air advection decreasing with height. So that's the only one that talks about the profile of heating. The Hirschberg-Fritsch equation says that changes in the height are due to the heating above the location, with the higher the better. Whereas Pedersen-Sutcliffe says that changes in the vorticity at the surface are due to heating above the location in question, as long as it was under the level of non-divergence. It's got that inverse pressure weighting as well in Pedersen-Sutcliffe, so the higher up in the atmosphere that heating happens, the better. It does have to be a local maximum of the heating, because you got a Laplacian there in Pedersen-Sutcliffe. All that makes good sense. And then the Zwack-Akasi equation on slide 93 tells us that the heating at any level of the atmosphere above the surface contributes more or less equally to cyclogenesis at the surface, but it does have to be a local maximum. It's the Laplacian of the heating, so it only works if you have non-uniform heating. You have like a local max or a local minimum of your heating. Wow, that's a whole lot of stuff to know. Now, remember back on Blue Line, we've got that giant handout that kind of summarizes the 4 development equations and what they say about vorticity and what they say about heating and so on, and how they measure cyclogenesis and so on. Go study that handout again, and that will help you understand what's going on the final. Now, I'm also going to have that review sheet and so on that helps you understand the level at which you need to understand this material on the final. All right. That's all I need from you guys for today, and please let me know if you have any questions, and we will have a 3rd review as well covering the material from Module 2 of the course.